Last thing we want to talk about with solids is actually classifying solids. So we know that the properties of a solid can be predicted, the relative properties of a solid. Is it really hard? Is it probably not very hard? Can be predicted based on the type of solid it is. So is it a metal? Is it ionic? Is it molecular? Or is it a network solid? And so we want to be able to classify our solids if you're given a molecular formula, make some predictions about the properties. And we know that the types of solids are going to be based around, what is holding the molecules to the solid together, and that kind of is going to then inform, or allow us to make this classification, right? We need to figure out what type of solid it is based off of what's going on, what chemistry, what physics are holding holding the solid together in its rigid structure. And so we're going to need to use our friend the periodic table to answer questions like, is it a metal? We know that we have this dividing line, this step right here, that we have our non-metals on this side and our metals over here. The color coding you can see is based on that. We can also use those sorts of things to determine is something a covalent compound, which would mean it's only non-metals bonded together. Is it a ionic compound, which means it's a metal bonded to a non-metal? Is it just a bunch of metal atoms? So we're going to use these ideas of classifying compounds that we've seen previously, ionic versus covalent, just kind of expand them out to talk about the types of solids that we're looking at. So let's look at an example. We want to classify each of our solids. I have H2O, ice, Ag3SN, carbon in the diamond form, and CaF2, calcium fluoride. So when we're going through this process, there's kind of a lot of different ways we can do it, but I'm going to give you like a set of questions that we can kind of narrow down what we're looking at. So the first thing we can figure out is this compound a metal? That's just using the periodic table. Is it only full of elements that are metals? Is it an ionic compound? That would mean I have a metal bonded with a non-metal. Does it form molecules? So if it's not a metal and it's not ionic, it has to be covalent. So now at this point in time, I want to see, is it a molecular solid, or hopefully it's a network solid? It's harder to predict what is a network solid. So basically, does it form molecules? That question is, can I draw a Lewis structure? So if you can draw a Lewis structure of the molecule with an end, then you're done. I'm going to start with H2O as ice. So the first question we want to ask is it a metal? And how we can always start, where we always need to start, is finding the atoms on the periodic table. So hydrogen is number 1 up in the top left. Oxygen is number 8. These are both nonmetals. Hydrogen's a bit tricky over on the left side, but it is raised off to demonstrate that it's a nonmetal. These are both nonmetals. And so that tells me that no, this is not a metallic solid. In order to have a metallic solid, all atoms in the compound, all elements need to be metals. Is it an ionic compound? No. These are both nonmetals. Both non or all nonmetals in the compound tells me it's a covalent compound. So it is a covalent compound. Does it form molecules? And so the question there is basically asking, can I come up with a Lewis structure that is finished, stable, all that kind of stuff? And the answer is yes. This is the Lewis structure for water. My oxygen has 8 electrons, as I'd expect. The hydrogens have 2, as I'd expect. This is a stable molecule. This is a stable Lewis structure. So yeah, ice is a molecular solid. It's made of molecules of water. Ag3SN. First question should be, is it a metal? Want to find them on the periodic table. Ag is silver, Sn is tin. Those are both metals. So because they're both metals, then it's just a metallic solid. If you take metals and mix them together, you still get a metal. That sort of sea of electrons is still going on. There's no bonding to exist here. There's nothing driving different types of bonding to form. They're just going to form metallic bonds as they were doing with themselves. So still going to be a metallic compound. It doesn't matter how many metals are in the compound, it's still a metal. It's a metallic solid. Carbon as diamond. Is it a metal? Find it on the periodic table. carbon is a nonmetal, so no, it's not a metal. It can't be an ionic because it's a nonmetal. And in an ionic compound, you need two different things. This is an element, right? This is just carbon as an element, and that cannot be an ionic compound because it's only one type of element. So nope, that is not ionic. Does it form molecules? Well, let's see. Can we draw a Lewis structure? It's just carbon. So if we draw the Lewis symbol for carbon, it's got 4 dots on it. It's got 4 lone electrons, but that's about it. Carbon by itself cannot form a stable Lewis structure. So what has to happen is it has to keep forming bonds to 4 other carbon atoms. So basically, diamond just forms, carbon just keeps forming single bonds with other carbon atoms. You just get a network that eventually forms out of that. But no, this is not going to be molecular, and so kind of by process elimination, it's going to be a network solid. You can't draw the Lewis structure of a network solid because it's the size of a crystal, right? It's just hundreds, thousands, millions of atoms arranged in a certain pattern. You're not going to be able to draw that. Also, you can it is useful just to know diamond is a network solid. That's the most common one that is talked about. CaF2, calcium fluoride. Find them on the periodic table. Calcium is a metal, fluoride's a nonmetal. So because there's fluorine in there, and that's a nonmetal, this thing is not a metallic solid, right? It would have to be all metals in there. But it is an ionic solid because this is an ionic compound. I have a metal bond in the compound with a nonmetal. That's a sign that this is going to be an ionic compound. This is the crystal kind of base unit cell of the crystal where the calciums and the fluorides are arranged in a certain way. You'll notice it's different from the sodium chloride. It's not perfectly kind of square because there's 1 calcium for every 2 fluorines. So you do need to kind of adjust to that. There's kind of fluorine rich or fluoride rich with different patterns, different structures where they're maximized. You'll note that there's not a lot of calcium touching other calcium. It's a lot of calcium touching the fluorines. Opposites attract. Participation 9.1, question 3. Which of the following solids are conductive? A, Zr, B, Si, C, NH3, and D, Cu, Zn. This is the third question on participation 9.1 due Tuesday, September 1st at 11:59 p.m. over on Blackboard. Link to the assignment is right below the document where these videos are posted. Again, which of the following solids are conductive? Zirconium, silicon, ammonia, and then copper, zinc. Okay, got a question on participation 9.1 in this video. One more video left in this set. Looking for any final questions to participation 9.1 and to finish up chapter 10. See you in that last video. Bye.